Okay, in this video, we're going to look at minimum connector problems and trees. This is a way of finding the easiest or maybe cheapest way to connect a set of nodes. That might represent things like, power lines between different houses, for example. And we want the minimum amount of wires we want to use to connect all of our houses. Yeah, we could also think about, a post who wants to go the minimum distance to deliver all the passes to all the houses. So what is a tree? It's a special type of graph or network where you've got each vertex being connected by exactly one path. So, if I added an edge like this, that is no longer a tree. And if it's a spanning tree, then all of the vertices in a graph are connected. So if we have a look down at our little example down here, we're trying to connect this up, and we want all of our work sites here connected to electricity. So, one way to do it is just simply like that. But, there are other ways. So we get rid of that. There's various different trees. But the main thing is if we want a spanning tree here, we need only all of our vertices connected, and just that would be a different one. I think I've got on the next slide a few. There's another one. So yeah, many ways to do this, but a tree with n vertices. So we'll have n-1 edges if it's a spanning tree, and even fewer if it is not a spanning tree. So our minimum spanning tree is we're connecting the whole graph and it has the lowest weight. So that might be cost or distance. And so, here we've got a network where the minimum spanning tree is highlighted. I'm going to show you Prim's algorithm, which is a way to find it. I'd say Prim's algorithm is one of the easier algorithms to learn in general maths, which is nice. And so, if you'd like, you could pause the video, take a screenshot of this process if you wanted to have something in your bound reference to refer to. But I'm just going to show you some examples, and hopefully that will help you understand it. So here is one. So it doesn't actually matter where we start. We can just make any edge the starting one. So I'm going to start here, and we're going to say, okay, so I need with Prim's algorithm, you're just adding edges that are the lowest weight one. So if you notice that 2 is the lowest of the 3 possible ones there. So we're going to add that. And then from here, it's always just the lowest that is already connected to your tree. So here we can see, well, the lowest one we could connect is this 3. Yeah. And then lowest from everything connected, well, there's a 2 down here. And then lowest from everything connected, another 2. So we'll take that. Now, and the next thing we've got, I reckon the lowest, see, we could hypothetically think about connecting this one, but actually that is not going to help us, right? Because that's going to stop it being a tree. So what we're going to do is we're going to add this 3 down here. That would work. Then what we've already connected all of those, and so what the only thing left to do is connect this along the 4. I'm not going to use the 5s because they are too big. So if we wanted to get, well, what's the minimum amount of whatever we need to use here, whatever our cost is, we would just add up all those edges that we've connected. Next slide, we've got drawing of what it would look like. And this one actually I think looks slightly different to mine, but what you'll find is it's just we've swapped this 3 and 3. So it's going to have the same minimum weight. And they're equivalent in terms of cost. Okay, let's try a bit of a harder one. So again, it doesn't matter where we start. Maybe I'll start here. And okay, so the minimum is out of 10 and 8 is the 8. Then here we've got a 4. And we're looking here, you could probably do this 7. That's going to be the next smallest one. I just circle these to make it a bit easier. I reckon the 6 is going to be the next lowest weight thing to add to our network. From there, I think this 7 is the next lowest weight. And we've got this 5 that we could add. We've got this 6. And then finally, we need to add this, and the lowest weight we've got is this 8. So all of those things, we've got every vertex added in with our minimum spanning tree. And if we wanted to get the total weight, we could just add it all up. So that is Prim's algorithm.